Next, let's look at the genetic algorithm. In the genetic algorithm, we have an input, which is the population, and we also have a fitness function. At the end of the algorithm, we have a return, which is an individual. So population is the set of individuals or chromosomes, and fitness function is that function which measures the fitness of every individual chromosome. So let's look at its loop. So it has an outer loop over here, repeat until, and we see how it works is, it says new population is an empty set. You start out with an empty set. Next, you take an inner loop where it repeats to the size of the population. There are two variables x and y, and they are initialized by random selection from the population using the fitness function. Then we apply a mechanism which is called reproduce. Now, with a small random probability, we also apply something called mutate. We'll see in a moment. And then whatever happens afterward, this child is added to the new population. And then finally, we move over the old population to the newer population. And this repeats till we got the best possible individual in the population according to our fitness function. We also want to take a look at the reproduce function, which takes it two chromosomes and returns one individual. So what happens is we divide the number into two and then take the two substrings and interchange them. And based on that, we find out a new individual. Now let's look at the genetic algorithm from the perspective of its internal working. So you can think of the genetic algorithms as a stochastic local beam search where the successors are generated from not just one but from a pair of states. So if we look at the genetic algorithm for an Nquing problem, each chromosome contains the states of the queen. So if we have an 8 by 8 board, and if we place the first queen on the second position, so here is the example, the second queen on the fourth position. Next we see that the next queen is on the seventh position and so on. So this can be evaluated in terms of the number of conflicts. So let's suppose we get to this number, which is 24. And if we look at the fitness function, we can say this is 31% fit and so on. The lesser number of conflicts in this case, so it's got just 14%. So in the genetic algorithm, we break these chromosomes at different locations. So 327 and 48552, we switch them and we get to these new chromosomes, and this mechanism is called crossover. So we started with fitness, we did selection, and then we from these pairs we did crossover, and finally we were able to do mutation. What is mutation? So a small number of these algorithms we keep changing randomly. So this chromosome, this is something we did in mutation. So this was 1, but we just changed it to 7. It's called mutation. If we look at the genetic algorithm from the perspective of Nquing problem, we see that this works because each of the substrings are essentially manifested into the problem itself. So you see here, these are portions of the string, and these actually represents the positions of the queen. So if you take a look at the yellow part, this yellow part and this yellow part, they just can be combined in the form of a new chromosome. So this is very similar to evolution, although the evolution is more complex because it actually encodes real genes which contain the replication mechanism itself.